of this matrix, since it's triangular, upper triangular matrix, so that the determinant will be, its property will be the product of the entries of the main diagonal, so we get lambda minus 3 cube, isn't it? Yes, Taiba. So now let's check eigenvalues. We take p lambda equals 0, means lambda minus 3 cube equals 0, so we get only one eigenvalue, lambda equals 3. Unique eigenvalue. It's repeated how many times? Repeated, very good, 3 times. This one we call it multiplicity. Multiplicity means the eigenvalue is repeated how many times? So now let's find, can we say that A is diagonalizable? We don't have 3 distinct, so we don't know. We have to move to eigenvalues. Let's find the eigenvalues. So for lambda equals 3, correct guys? We have to find all eigenvalues. If we have 3 eigenvalues, because here the matrix is 3 by 3, so if we have 3 eigenvalues forming a basis, in this case we get an we get a diagonalizable matrix, correct? Which part, Hamad? We didn't do anything, just we found eigenvalue. Yes, because look here, solve this one. Lambda minus 3 cube equals 0, so lambda equals 3. Here, if you do cubic square, you will get lambda minus 3 equals 0, so lambda equals 3. You understand it now? Okay. Now let's find eigenvalue. Hopefully we have 3 linearly independent eigenvectors. So here we solve lambda I3 minus A V equals 0. Now this V here, is it ABC or AB? Very good, ABC, because it's 3 by 3. So we get the augmented matrix. Now here, put instead of lambda, put 3. So we get 0, negative 1, 0, and 0. 0, 0, negative 1, 0, and last row all zeros. To make this one leading 1, we divide by minus 1. R2 divided by minus 1, so we get 0, 1, 0, 0, 0, 0, 1, 0, and all zeros. Now here we have ABC, leading 1. Which one is free? A is free. Do we have another free variable? No. So we will get only one eigenvector. B equal how much? 0, and C equal 0. Right? Very good. So V, which is ABC, will be A 0, 0. What do we take? We take A equal 1. we get, you can take any value, we get V1 equal 1, 0, 0, the unique eigenvector. So A, is it possible A is diagonalizable? Not diagonalizable because the set of eigenvectors is not basis. The set of eigenvectors, how many eigenvectors do we have? What? One. It cannot be a basis for R3. Impossible. How many do we need to get a basis for R3? How many vectors? We need 3 linearly independent. Here we have only 1. Impossible. We need number 3 and linearly independent. Not only number 3, we need 3 vectors linearly independent, which is here we have only one case. We have only one vector, so impossible. Is it clear, guys? Please take screenshot. Keep it with you. Done? Okay. Let's see the second matrix, B. So here's the same. Let's find eigenvalues. If we have 2 distinct eigenvalues, means 2 different from each other, immediately it's diagonalizable. So here, P lambda, determinant lambda I2 minus B. So it will be lambda plus 2, minus 2, minus 5, lambda minus 1. So it will be, we multiply the main diagonal, minus the off diagonal, it's minus 5 multiplied minus 2, it's 10, so minus. Multiply, open the bracket, so we get lambda squared minus lambda plus 2 lambda minus 2 minus 10. So P lambda, it's equal to lambda squared plus lambda minus 12. Correct, guys? Very good. Very good. So we see the eigenvalues. To see the eigenvalues, we take P lambda equals 0. So lambda squared plus lambda minus 12 equals 0. So lambda 1 equals 3, lambda 2 equal minus 4. Do we have distinct eigenvalues? Very good. So we have 2 distinct eigenvalues for A, which is M2 by 2. So exactly here 2 and 2, the same. So A is diagonalizable. Too simply. Is it understood, guys? You see, it's very easy. Diagonalizable. If we have distinct, how many we need? Since it's square matrix, number of rows equal number of columns, for example, equal n, we need n distinct eigenvalues. Here, 2 by 2, we need 2 distinct eigenvalues. We have it, so it's diagonalizable. Now, if it's not distinct, in this case, we need to find the eigenvectors if they form a basis or not. We will do an example about this one. Yes, for sure. So here, what is this matrix here? 2 by 2 or 3 by 3? 3. So if we have 3 different eigenvalues, if we have 3 distinct eigenvalues, then it's diagonalizable. If not, we need 3 different eigenvectors linearly independent. Okay, guys? So let's check for this matrix if it's diagonalizable or not. So here we want to find if it's possible to find matrix P, non-singular matrix P, such that P minus 1 P minus 1 AP is diagonal, means is equal to, if this one equal to D, diagonal matrix, means if it's diagonalizable or not. So let's check P lambda. Determinant lambda I3 minus A. So it's equal lambda minus 1 minus 1 minus 2 0 lambda minus 1 0 0 minus 1 lambda minus 3. So now we do cofactor expansion along the first column. It has 2 zeros, or we can take the second row, no problem. We take the first column, so we get lambda minus 1. Determinant, we hide first row, first column. So we get lambda minus 1, 0, minus 1, lambda minus 3. So what do we get? We get lambda minus 1. And here, what's the determinant of this matrix? Diagonal of diagonal is 0, so we get only lambda minus 1, lambda minus 3. So we get lambda minus 1 squared, lambda minus 3. So how many eigenvalues do we have? Lambda 1. How come 3? Lambda here. This factor equals 0 means lambda equal 1. Second factor, lambda minus 3 equals 0, lambda 2 equals 3. Only. How come 3? From here you will get 0, you will get lambda equal 1. Here you will get lambda equal 3. And guys, 1, lambda 1 equal 1, it's repeated how many times? 2. Yeah, because here, look, it's repeated twice. Very good. So now, can we say that A is diagonalizable? Do we have 3 distinct eigenvalues? No, so we don't know. Let's check if we have 3 linearly independent eigenvectors. So for each eigenvalue, let's check the eigenvectors. So let's use another color for lambda 1 equal 1. So we solve lambda 1 I minus A V equals 0. Tell me here, this V, is it ABC or ABCD or AB? ABC. So no need to write it, we know. So put, instead of lambda, put 1. So put 1 here, we get 0, minus 1, minus 2, 0, 0, 0, 0, 0, and 0, minus 1, minus 2, 0. So to simply here, R2 instead of R3, because we don't know if it's like diagonalizable or not. Here you have only 2, but the matrix is 3 by 3. So we don't know if it's diagonalizable or not. If you have 3 here eigenvectors, 1, 2, 3, for example, or 1, 3, minus 1, different, yes, then you stop, it's diagonalizable. But here we don't know, okay? Okay, so we get 0, 1, 2, 0, 0, negative 1, negative 2, 0, and all zeros. And to simply we do R2 plus R1, 0, 1, 2, 0, 0, 0, 0. Okay, so now we have ABC. Here I have reading 1. Here 0 equals 0. Here 0 equals 0. Just a second. So, what are the free variables, guys? A and C, very good. Very good, A and C. A is free, C is free, and B equal what? B plus 2C equals 0, so B equal minus 2C. Pay attention, not minus 2. What's the number? False. So, V, which is ABC, so A is free, C is free, B equal minus 2C. Now, as we did for subspace, guys, remember the basis for subspace, we split it into A and C. A 0, 0, plus 0, minus 2C and C. And now put A outside, A 1, 0, 0, plus C 0, negative 2, and 1. So look here, we get V1 and V2, two eigenvectors, V1 and V2 eigenvectors for which lambda? For lambda 1, the same equal 1, right? So we get two eigenvectors for lambda 1, which is good. Now we need the third one from lambda equal 3, right? Okay, if you want, take screenshot, guys, to find lambda, to find V3. or I will write here. Okay. Now for lambda 2 equals 3, we solve lambda 2i3 minus a b equals 0. So yes, Muhammad, cannot hear me? Okay. So here I have leading 1 to cancel this one, R3 plus R2. So we get 1 negative half, negative 1 0 0 1 0 0 and all zeros. Now here we have ABC, leading 1, and here 0 equals 0. In this case, guys, what are the free variables? How many free variables do we have? Only C is free, very good. B, so B plus 0 equals 0, so B equals 0. And A here, since B is 0, forget this one, so A minus C equals 0, so A equals C. So V, which is ABC, it's equal to A, which is C, B 0, and C is the same. So we take C equal 1, different than 0, we get V3, which is 1 0 1. Eigenvector associated with lambda 2 equals 3. So the set of eigenvectors, so far we have the set of eigenvectors are, so the set is V1, which is 1 0 0, V2 0 2 1, I remember, 0 negative 2 1, and V3 1 0 1. So here, look, we have a possibility to get a diagonalizable if V1, V2, V3 is linearly independent. How to check if they are linearly independent or bases? We take determinant V1, V2, V3, it must be different than 0. So it's equal to 1 0 0 0, negative 2 1, 1 0 0, 1 0 1. Again, we do cofactor expansion along the first column, so we get 1 multiply height first row, first column, so negative 2 0 1 1. Here it's triangular, so it will be minus 2, different than 0, so V1, V2, V3 are linearly independent. Finally, A, is it diagonalizable or not? Since V1, V2, V3 are linearly independent, is diagonalizable. Why? Because the set of eigenvectors form a basis. The set of eigenvectors form a basis for R3. Understood, guys? Too simply, very easy. Please take screenshot. I want only this one. To take it for the second slide. Yes, we did it here, lambda equal 1, look. We get two vectors. Since here we have two, so we have a possibility to get two vectors here. Look, we get 1, 2, because here it's 2. Okay, Hamad? We can get 1 or we can get 2, no problem. We can get maximum 2, 1 or 2. Now, guys, look at the question. What's the question? We didn't answer the question. Find non-singular matrix P. How to find this matrix P? We have seen this one before. So here we have the set of eigenvectors. So the matrix P is P equal V1, V2, V3, which is 1, 0, 0, 0, negative 2, 1, 1, 0, 1. This one was from the first slide. Okay, guys? And who knows what's the matrix D? So here we know if A is diagonalizable, so A is equal to P, D, P minus 1. P is this one. Who knows how to get the matrix D? What do we put, guys? So here we put V1, we put lambda 1. V2 is corresponding also to lambda 1. V3 is corresponding to lambda 2, right? We put them by order. V1 corresponds to lambda 1. V2 also corresponds to lambda 1. V3 corresponds to lambda 3. So we get lambda 1 was 1 and lambda 2 was 3. Correct? Is it clear, guys? Very good, Nora. Please, guys, is it clear for all of you? We still have an application. Why do we need eigenvalues? Why do we need eigenvectors? Why do we need diagonalization? We have one application. We'll do it right now. Okay. Basically from 3, 5, 7. But as you know, for linear algebra, it's basics. So you need multiplication of matrices, you need inverse, you need determinant. So basically, you have to know everything about it. REF, you are using always REF, right? Look, for example, here, this example. Look, you need determinant. Here we are using determinant. Cofactor expansion. You need REF. You need, for example, here again, determinant. Spanning bases. Here we use this property. All linked together. Very good. But yes, basically 357. And everything related to 357. Very good. Okay, guys. So here, what do we have? We have exercise 3 from the textbook. We have D. What's the form of this matrix, guys? Yeah, 2 by 2, but more important is diagonal matrix. Look, it's diagonal. We have diagonals, entries, and everything else 0. So always, guys, to find D9, if D is diagonal, then D to the power of n is obtained by raising the entries of the main diagonal to the power of n. The power n. Okay, guys? So here, how to get d to the power of n? Since it's diagonal, so just we have yes, very good. We have to take the entries to the power of 9. So we get 2 to the power of 9, 0, 0 minus 2 to the power of 9. And this result is true because the matrix is diagonal. So here we get 512, 0, 0, negative 512. Okay, guys? Very good. Now, what will happen if the matrix is not diagonal? We can still use diagonalization, guys, and this is why it will be question. You will ask your questions, Abdullah. Or even if we do review, it doesn't mean the same questions for the final. Maybe I will pick different exercises, but not necessarily for the final, okay? Okay. Look, guys, this matrix, is it diagonal? Not diagonal. So we cannot apply, we cannot say it's 3 to the power of 3 minus 3 to the power of 3 false. But maybe it's similar to a diagonal matrix. If A is similar to a diagonal matrix, what does mean similar to a diagonal matrix? Means we can write A as P, D, P minus 1. In this case, we remember the first slide, we said how to get A to the power of n. We do D to the power of n. And for this one, it's easy. We raise all entries of the main diagonal to the power of n, right? So let's check if it's diagonalizable, and we can write it as A equal to PD P minus 1. Let's check all eigenvalues and all eigenvectors. Let's erase the page here. You understand the idea, guys? Okay. Now, let's solve it. P lambda I2 minus A. So it's equal to lambda minus 3, 5 minus 1, lambda plus 3. So we get lambda minus 3 lambda plus 3, and here minus 5, so we get plus 5. So here, who knows immediately what do we get when we have lambda minus a minus b, a plus b, what do we get? We know that a minus b, a plus b is equal to what? A squared minus b squared, right? So here we will get lambda squared minus 3 squared 9 and plus 5. So we get lambda squared minus 4. Now let's check the eigenvectors values. So p lambda equals 0. Lambda squared minus 4 equals 0. So lambda 1 equal, lambda 2 equal what? 12 minus 2. Very good. So 2 and here minus 2. Now, is it diagonalizable? Why? Because we have two distinct eigenvalues. Very good. For A, which is 2 by 2. So here the same, 2 and here 2. So A is diagonalizable. So we can write A is equal to P D P minus 1. D, we know how to write D. D is equal to lambda 1, lambda 2, 0, 0, which is 2, 0, 0 minus 2. But how to find P? P, it will be V1, V2, correct? So how to find it and how to find P minus 1? So let's do it step by step. So let's find V1. So for lambda 1 equal to, we solve lambda 1 I2 minus A V equals 0. So let's write the augmented matrix. Put instead of lambda, put 2. 2 minus 3 minus 1 and 5 minus 1 and 5. Minus 1, 5. Minus 1, 5. So here R1 divided by minus 1. So we get 1 minus 5, 0. Negative 1, 5, 0. And R2 plus R1, 1, negative 5, 0, 0, 0, 0. AB, leading 1, and here I don't have any leading 1, so which one is free? B is free. A equal what? Move minus 5 to the other side, so we get 5 what? B, 5B. So V, which is AB, will become 5B and B. We take B equal 1. If B equal 1, so V1 it's equal to 5, 1, correct? Eigenvector associated with lambda 1 equal to. Now let's do for lambda 2 equal negative 2. Guys, do you understand? Are you understanding everything? Wonderful. Again, we solve lambda 2 I2 minus A V equals 0. 0, 0. Put instead of lambda negative 2, minus 2, minus 3, so minus 5, 5, minus 1, minus, and 1. So minus 5, 5, minus 1 and 1. Here, R1 divided by minus 5, 1, minus 1, 0, negative 1, 1, 0. R2 plus R1, 1, negative 1, 0, and all zeros. Again here, A, B, B is free, very good. A equal B, very good. A, B, so A is equal to B. Take B equal 1 different than 0, so V2, which is 1, 1, is N. Why we say N means it means we have many. We can fix any B to get another eigenvector. Is an eigenvector, is one of the eigenvectors associated with lambda 2 equal to negative 2. So guys, finally P, which is V1, V2, it's equal to what? V1 is 5, 1, V2 is 1, 1. Now, what's missing? P minus 1 equal what? So too simply, P minus 1 is 1 over determinant of P, adjoint of P. Correct? Let's check. Determinant of P immediately, guys. It's equal to what? 5 multiply 1, 5. Minus 1 multiply 1, 1. So it's equal to 4. Now let's find the adjoint. So P equal to 5, 1, 1, 1. Determinant of P equal 4. Adjoint, we need P11, P12, P21, P22. Yeah, guys, P11, is it positive or negative? Why we are using this one? This one because adjoint of P is P11, P12, P21, P22. So plus P12 is minus, P21 minus, P22 plus. P11 we have to hide first row, first column, so we get 1. P12 hide first and second column, so we get 1. Now P21 hide second and first, 1. Second and second we get 5, so we get 1 minus 1 minus 1, 5. So P minus 1, it's equal 1 over determinant of P adjoint, means P minus 1 is equal to 1 over 4 minus 1 over 4, negative 1 over 4, 5 over 4. So A, it's equal to P, D, P minus 1. And we have everything here. And A9, since we need A9, it's equal to P, D9, P minus 1. Correct, guys? So A9, it's equal to P. Where's P? It's 5, 1, 1, 1. D to the power of 9. Yeah, formula. This one is formula adjoint, Hamad. Revised section 6.4. Adjoint P11, P21, P11, P12, P22. Usually we use it for 3 by 3. P11, P21, P31, P12, P22, P32, and P13, P23, P33. Okay? Section 6.3, 6.4. Or 6.3, I don't remember. 6.4. Now, guys, D to the power of 9, don't forget this one is 2, 0, 0 minus 2 to the power of 9, so it will be 2 to the power of 9, 0, 0 minus 2 to the power of 9. And p minus 1 is 1 over 4, minus 1 over 4, minus 1 over 4, and 5 over 4. So it will be 5, 1, 1, 1 times 5, 12, 0, 0 minus 512, 1 over 4 minus 1 over 4 minus 1 over 4, 5 over 4. So guys, instead of doing A multiply A multiply A multiply A 9 times, just multiply these three matrices. Multiply. Guys, can you multiply 5 times 512? What do we get? 5 times 512. Two, 5, 6, 0. And here, so row by column, minus 512. Here, 512. And minus 512. Can you multiply these two matrices, guys? Multiply row by column, and give me here the answer. Please do calculation. Okay, very good. 768. And 256. Negative. You mean here, right? Here 256. And here negative 1280. And finally, minus 512. 12, yeah. That's very good. Is it understood, guys, all of you? Please, do you have any question? Because now we are done with section 7.2. Yeah, it's a little bit long, yes. Yes, Abdullah. Okay, here. Yes, Muhammad, what do you want? We did step by step to first to prove that A is diagonalizable. Here we prove that A is diagonalizable, so we can write A as dP minus 1. Why? Because we want to use this property here in the beginning of Tuesday. Where is it? Yeah, we said if you have A equal to P d P minus 1, in this case, n A to the power of n is equal to P d to the power of n P minus 1. And d, we know it's diagonal. So how to find d to the power of n? It's lambda 1 to the power of n, lambda 2 to the power of n. So just you put here to the power of n, right? Because it's diagonal. Okay, Muhammad? So we want to use the fact that A is diagonalizable to use this property here, to use this one, to use this property. So the most important for us is this one. So to write this one, you need P, you need D, you need P minus 1. For D, you know it, it's lambda 1, lambda 2, right? And P also, you know it, it's V1, V2. So to find V1 here, we did, this is V1. We did calculation to get eigenvector V1. We get eigenvector V2. So now you have P. What's missing from the equation P minus 1? So we did the calculation to get P minus 1. So now I have A equal P d P minus 1, and I want to apply A to the power of 9. So you write P d to the power of 9 P minus 1. You have this one, you have this one, also you have this one because it's diagonal. You multiply, you get the result. Understood? It's a little bit long, you're right. You multiply matrix by matrix. What? How to multiply? You multiply row by column, as usually. This one you forget it from chapter 1? Yeah, row by column. Too simply. You multiply here. Where is it? So here you multiply row by column, row by column, row by column, row by column. And you get the answers. You forget it? Okay, that's it. Okay, guys, so I will keep the remaining time. Still have 10 minutes for your questions. If you have questions, please feel free and ask me. Chapter 3, 5, 7, and everything related to this chapter. Have a nice weekend. Thank you very much. Thank you, guys. Have a nice weekend.